You- Go for it.
Hello, everyone. This is Dan and Neil here. We are going to do a quick virtual run through of all the problems on the review session. So I guess we can jump straight into it. So here, the first problem is problem 1. This should be very similar to you. I believe it was homework 2, problem 14. But basically what we're going to do here is standard Cantor. We create our set X in X, where X is A, B, C, D, E, that's defined in the problem, where X is not in F of X. So basically, we're going to iterate through all of the functions provided, and we just want the set where X is not in F of X. So if you look at F of A has A, C, D, so it has A, so we don't want that. F of B does not have B, so we want B. F of C does not have C. F of D and F of E both reference themselves, so you don't include those. So super quick, but there is your set.
Perfect. Okay, so we're looking at number 2. So we have to sort the strings over the alphabet ABC in short Lex ordering. So they give us 5 strings to look at. I'll number them 1, 2, 3, 4, 5. So the way to look at short Lex is that you always prioritize, it's sorted by string length, and then afterwards it's kind of your dictionary sort. So you could convert them all to numbers and compare them. That's one way to do it. But if we just look at the lengths, we can also find out the answer too. So there's only one string with 6 letters in it. That's C with 5 A's. Yep, C with 5 A's. Then after that, we have all the 7 length strings. So the first one would be 6 A's, then a B. After that, we have, I think, this one right here, 6 A's and a C. The next one's going to be A, C, A, B. So these two are right next to each other in the short Lex language. And then after that, we have the last one, which is 7 B's. Cool. So that's how you do part 1. The second part, it's asking which string is preceded by 20 other strings. So this means it's basically asking you what word has short Lex number 2020. So we're asking for 2020 in base 3. So remember the algorithm that we did in class. We need to write 2020 in terms of a quotient and a remainder and for divisibility by 3. So I'll kind of write out the steps over here, and then we can convert it. So 2020 equals to 673 times 3 plus 1. Okay. Plus 2 plus 1. So yeah, we go through and then we take the quotient and then we decompose that in terms of what it is times 3. And then after that, we get a bunch of remainders. We convert them to the appropriate letter. So we get A, B, B, C, A, B, and we read bottom up. So our word becomes B, A, C, B, B, A. That's our word. Make sure as you're doing this that the remainder has to be between 1 and B and not 0. So in the case of the 24 over here, you can see it could be 8 times 3 plus 0, but instead we used we had a remainder of 3 over here, so it turns out to be a C. And as a result, the next quotient will be 7 and not 8. And that's all you really need to look out for.
Awesome. Okay, so on to problem 3. This one, you don't have to worry about getting too creative or having a nice simplified solution. I just sort of took the cross product of two DFAs here, right? So as we go along the X, so let's first establish our start state here. As we go in this direction, we want to accumulate A's. And in this direction, we want to accumulate B's. And then we can sort of work our way across and make our DFA, right? So each time we see an A, and then each time we see a B, right? And so as you can see, as I construct this, that if you see this like an XY coordinate plane, which goes positive in the right and downward directions, that we are, your XY coordinate represents how many A's you've seen at this state and how many B's you've seen at this state, right? Cool. And so now you can see once we get here, we have seen exactly 2 A's and exactly 3 B's. Now, this has to be deterministic, so we can't just stop here. What happens if we see more than 3 B's? Well, we can just sort of hang out down here. But then A's have different behavior because we want to assert that there are exactly 2 A's. So we can sort of get like a trap state going on here where whenever we see more than 2 A's, we can just sort of accumulate them over here and then loop on all inputs. So don't worry about getting super concise and having a super creative solution. This should be just the bare bones, like the super easy, naive way to approach it. Okay. Problem 4. So let L be the language represented by the regular expression A union B star, A B B, A union B star. Okay, so again, if we see this A union B star on both sides of a string, then that basically just means we're looking for the pattern within to be contained inside the entire string. And that pattern is A, B, B. So the string, or the language that we are representing here is the language of any word that contains A, B, B. Okay, and so now to construct a DFA, when we're doing contains, right, we just have our little B, and then, we just want to loop on B's here. And then whenever we see an A, we start the pattern and we're looking for A, B, B. And once we've completed the pattern, we can loop on all inputs. And if we see any invalid, like if we see a B here, A, we want to return to our original state. And then since we're taking the complement of this, we want every time where the pattern has not been completed. So these states. And that's really all you have to do for 4. Let's see. Okay, problem 5. We have the language ABC, and we're looking to concatenate 2 words. So the way I would approach this is I would write DFA or just some finite automaton for W1, and then write one for W2, and then go through the construction provided in class to combine them. The construction you'll see is slides 9, and the slide is 31. So for W1, we want an even number of A's. So here we should have an accept state, and then whenever we see an A, we leave the accept state, and whenever we see an A, we return, and we don't care about the other letters in the language. So this is W1. Now to recognize W2, we would like the number of C's to be a multiple of 3. So again, 0 is a multiple of 3, and then our C's can just chase each other around. And then we loop on all other inputs. So now to convert this, to concatenate them together, from all the except states in word one, we have an epsilon transition to the start state of W2. And then W2 no longer has a start state, and there shouldn't be no except states in W1 because we need the pattern in W2 to occur. And so through this construction, we've concatenated W1 and W2. And you should try this on a variety of inputs to satisfy yourself that this works. Neil, you want to do problem 6?
Yep, I was muted, sorry. Number 6, we're going to be using a subset method to convert the NFA into a valid DFA. So let me just draw out the, why is it yellow? Okay. We have, what? I am so sorry, give me 1 second. Okay. Okay, we have 1 here. Epsilon 2 goes back, A, and then we have, oops, sorry, this is going the wrong way. It goes this way to 3. There's a loop on B over here, B, and then we have AB over here. Okay, so the first thing we need to do is understand that the set of states in the subset is not all possible subsets of the original NFA, namely because there's some combinations of states that can't be achieved simultaneously. So what we need to do is we need to first figure out the initial state and then build off of that. So let's create a table over here that describes one, the current state, and then where we transition to when we read an A or a B. Notice that we don't care about epsilon, and we'll just follow the epsilon trails when we reach a state. So our initial state is 1, but observe that there's an epsilon transition to 2. So 1 and 2 are actually the initial states that the threads will be in when the NFA starts. So we start with the 1, 2 over here. And when we read an A, the 1 thread goes to 3 and the 2 thread goes to 1, which in turn goes to 2. So 1, 2 points to the subset 1, 2, 3. When we read a B, the 1 thread dies and the 2 thread also dies. So this goes to the empty state. Now we also need to have an empty state transition, which keeps going to the empty state so there's no alive threads. And then for 1, 2, 3, if we read an A, we can reach 2. 2 goes to 1, and the 1 thread will go to 3. So we stay at the state 1, 2, 3. Sorry. 1, 2, 3. And when we read a B, well, the 2 state doesn't have any transitions. The 1 state doesn't have any transitions. But the 3 state stays at 3, and it also goes to 2. So the next subset will be 2, 3. Finally, for 2, 3, if we read an A, we go to 1, but 1 also connects to 2 via epsilon, and 2, 3, 2, 3. If you read an A, it stays at 2, and we also get 1. Yeah, that's right. Okay, so it's 1, 2. And then for B, if you read a B from 2, you go nowhere. And if you read a B from 3, then you go to 2 or 3. So this also is 2, 3, 2, 3. So we have no new unvisited subsets. So these 4 states are our Q right here. These are our Q over here. Our final state is all subsets that actually contain a 2. So namely, they're all accepting in nature. So you'd say everything's except for the empty set, of course. 1, 2, 1, 2, 3, and 2, 3. Our starting state, as we mentioned, was the first one we wrote down, which is 1, 2. Oh, I should not put another thing there. Cool. And then our delta transition is right over here, this nice thing. So make sure, as I said, your Q is all reachable states over here, not all possible subsets. And that should be all. Okay, number 7, write a regular expression describing the language W does not contain 2 consecutive Bs. So when we see W does not contain 2 consecutive Bs, what we can view this as is every B is going to be preceded, or every B is going to have A's on opposite sides of it, unless it's the first word in unless it's the first letter or it's the last letter in a word. So there's a bunch of inspiration that you can look at in the recording where we talk about words that might help us generate a strategy. I'll kind of list them out. We thought about an A star that doesn't contain 2 consecutive Bs. We're thinking about other words like B, A, B, A, B, these kind of things. And here was one possible regular expression that we came up with. So the observation was that every B is going to be, oh my God, it's happening again. One sec. Okay, perfect. The observation was that every B has an A that's preceding after it, unless it's the first, unless it's the last B in the sequence. For example, BA over here, there's a B over here, but this B is the only case where that's not true. So realistically, we can have some number of A's to start out with, and then a B, and then a BA, and we can represent this as BA union A star. So notice that if you pick A's first and then the BA, then you can get some word that starts with A's, but you can never have 2 B's next to each other in this thing. Now, of course, looking at example number 2, it's impossible to generate this last B. So since we know that this word always ends in A or is empty, we can either terminate it on an A by keeping the expression as is, or we can concatenate a B. So what we'll do is we'll concatenate B union epsilon, and as a result, oh my God, hold up. Yeah, and then we'll concatenate B union epsilon. So notice that the A star can be generated with just this first part, but in order to generate something like 2, we can actually leverage the B and B union epsilon to generate that last B. So this is just one example of possible regular expressions to generate, but hopefully you can see the kind of like inspiration that we got for generating this. Okay, cool. On a similar note, we're also looking at 8, which is asking us to generate W, which does not contain AAAA. So in order to do this, we can also generate words that should exist in our language. For example, we want to have A, AA, AAA. These are like our base cases. We also want to contain B star because that doesn't have any A's in general. We also want to have things like, you know, random strings like BAAA, BA. There's also cases where the A's start out in the beginning, like this, AAB, AAA. So we have A's in the beginning and A's in the end. So either way, the observation is that, so we're going to have some number of B's at the beginning, and then we can use each B afterwards as a delimiter to segment the set of A's. So I'll use a different color here just to show how we can use the B's to segment the A's. So here's one group of A's, here's one group of A's, here's another group of A's, and then here's like the trailing end A's. So they don't have a B with them, but we can handle that case similar to how we did last time. So our regular expression starts off with B star, and then after that, we can either read up to 3 A's within one of these tiny groups. And all we need to do within the star is guarantee that it always ends with a B. We'll handle the last set of A's separately. So I put oh, that's definitely not enough space. I put a star here as such, and then I have, I have B union AB union AAB union AAAB all starred. So this represents all cases, namely these are two adjacent B's to each other. Oh, sorry. So we have this is 0 A's, this is 1 A, and then this is 2 A's, and this is 3 A's. Now, finally, we know that since each of these clauses ends with a B, we know that at the end of this expression, it must end with a B. So we are free to tack on and concatenate up to 3 A's. So we can either have nothing if it ends in a B, we can have a single A, we can have 2 A's, or we can have, oh my God. Okay, we have 2 A's, or we can have 3 A's that end our expression. And that all concatenated together. So B star, this star, and then the A epsilon union A union double A union triple A represent all words that do not contain 4 A's in a row.
Awesome. Okay. So problem 9. How I like to look at this kind of problem is just to sort of break it down into bite-sized little atomic pieces and then try and find ways that I can sort of combine them up as I simplify. So let's look first at B union B A star, right? So what I'm looking for here is something like redundancy or some sort of closure. So what this little bit describes is B followed by 0 A's. And this is B followed by greater than or equal to 1 A's. And what we see here is that 0 and greater than or equal to 1, we can combine this. This entire phrase is B and greater than or equal to 0 A's. And greater than or equal to 0 A's is described by a star. So what we have here is B A star, and then I'll include the rest of the expression here. So this is what we've sort of reduced down to. And so now what you can sort of see being described here is that we have some quantity of A's, it could be 0, it could be as many as you want, and then B's followed by some number of A's. And the number of A's can be varying however you want, but each B can be paired with all subsequent A's. So anywhere you want to terminate any string, you'll have a way to do that based on this regular expression. If you want to have 0 B's, you can just loop this A star infinitely. If you want to have exclusively B's, you can ignore the A star and you can just have the B with 0 A stars. You can make any word over the language A, B with this string or with this regular expression. So what we've just made here is just A union B star. And you're pretty much never going to get more simple than describing the entire language. It's going to be impossible to simplify beyond this. Okay, now problem 10. Problem 10 is very interesting. The standard way to do it that you should be comfortable with is to create GNFAs and convert all of the NFAs provided into regular expressions. However, I think you're going to find that there's an easier way to do it. So hopefully you have the document up and you're going to be able to follow along with me. And I'm sort of going to operate under that assumption. So first of all, if we're looking at the regular expressions, we see that they all begin with epsilon union something. All that's really going to indicate to us is that the start state should be an accept state. And you should be able to convince yourself that that's true for A through E. And then our other pattern is going to begin with a 0. So as you can see, all of them have a 0 that loops up to the top left state of the respective NFAs. And now is when we get to a little bit of variance between each NFA. So we notice that there's a big pattern that's starred. And what that always indicates that you should be familiar with converting GNFAs to regular expressions is that that is a loop. So we should be looking for loops. So for example, if we look at A, we have from the top left, we have a loop 0, 0 going down and back up. And then we have 0, 1 star 1. So we're looking for that star pattern in the middle of our regular expression to match 0, 0 union 0, 1 star 1. So that matches 1 and that matches 4. So A is either 1 or 4. Now we see that 1, for example, has a 0 after the loop, and we can see that a 0 takes us to an accept state. And then we have a 1 star. So if we follow 0 and then 1 star, we can see that A accepts. So 1 absolutely works for A. So 1 matches with A. All right, so now what else do we have? I am observing here that D is very similar to A. They have all the same transitions. The only difference is that A has an extra final state up in the top right there. So where D doesn't have that, that's actually going to be the difference between 1 and 4 that we narrowed it down to, is that 4 does not accept that 1 star, which indicates that loop on the accept state that A had. So D and 4 are going to match. Now, as I continue to move forward here, we can see that 1, 3, and 4, the regular expressions, all have the pattern 0, 0. But we've already matched 1 and 4, so that just leaves 3. So there should be one of the finite automatas between B, C, and E that has a 0, 0 loop, and that is B. And so we can match 3 with B. So now we just have 2 and 5. And we can notice the same pattern that helped us differentiate between 1 and 4 was that 5 only accepts the 1, whereas 2 accepts a 1, 0 star. So E has a loop on that 0 star that is an accept state, and C's 0 star loop is not an accept state. Thus, C will match to the one without the loop, which is 5. And then 2 is going to match process of elimination to E. So hopefully everyone understood that. You are more than welcome to use GNFAs on the actual exam. It's just that might take a little while to go through and simplify. So just reverse engineer the strategies you use for GNFAs to identify regular expressions from the diagram without having to convert it. Now we can go through one of those GNFAs conversion properties. Let's start off by drawing what we have. And if you're looking for the sample from the slides, GNFA conversions happen in slide 9E. Okay, so here we have an accept state, and then A and B go over to state 2 here, which loops on A. And we have state 3 here. And there we go. So this is our finite automaton that we start with. So step 1, we just want to convert it to a GNFA. So we introduce a new start state. We epsilon transition into the prior start state. And then we have all of our old transitions, except we replace things like A comma B with A union B, because we want to get into regular expression form. And again, nothing is an accept state in our prior set of states. Cool. And now we introduce a new except state, and we epsilon transition from all of the prior except states to this new except state. Beautiful. So now in the assignment, you are instructed to strip state 1. That is this guy right here. So to strip this state, what we want to do is we want to completely remove it from what we have and then repair. So see, I'm going to get this one out of the way and then write in its stead. So we still have our start state. And then you'll notice S1 has gone away. So we now need to find new paths to everything. So what I do when I remove a state is I take all of its in edges, so that being this edge and this edge, and then I run DFSs out to sort of repair all of their paths, because the in edges are the ones that are affected by the removal of that state because they can no longer get where they need to go. So let's look at this epsilon edge first. So it's got a couple options. It can epsilon down to the except state. So let's get that in there. Or it can follow A union B to get to state 2. Fantastic. And now we need to repair this edge, this A edge coming in from state 3. Okay, and I'll give you 2 and 3, so it's more explicit. So 3 goes into 1 with an A, and then it goes to 2 with an A union B, or it goes to 3 with to the except state with an epsilon. So again, we follow this route, and that gets us here, and we traversed just A, and then we also get to 2 following this pattern here, which is A and then A union B. Now you'll notice we already had a path to 2 here from 3 to 2. So we can just take this expression and union it with what's already there. And then everything else stays exactly the same. 2 was untouched. Beautiful. And again, you can see this 3 here, we still had this pattern. So that needs to be preserved. Next, we're going to rip state 2. So I'm going to take this old diagram out of the way here. And I may make a mistake. There is a lot going on here. I do apologize. So please follow along and convince yourself of all of the strategies I'm taking. And you should have complete and verified examples from the lectures that I recommend you refer to. Okay, so now we're ripping state 2. So we have this edge that we need to worry about and this edge that we need to worry about. So let's take the one coming out of S first. So coming out of S, we hit 2, and then continuing to DFS out, we hit 3. So we have S, and then to get to 3, we go A union B, and then we could loop here in perpetuity as much as possible. So we put an A star there because we could hit it 0 times, we could hit it 2, etc. And then we have our B. And that gets us to 3. And now our other in edge we have to consider is that A union B. So we get back up to 2, and this is ultimately going to be a self loop. So we have A union B, all of this concatenated with A star B. And then we still have this except state down here that takes an epsilon from start and an A union epsilon from 3. None of those have been affected. So finally, we need to write out our entire epsilon, our entire regular expression by removing 3. So we have S, and then we're going to have this massive transition. So first, we have this pattern. It's not going anywhere. It's not affected by the removal of 3. So we have epsilon union. We take the A union B, A star B. We concatenate it with this loop. A union B, A star B star. and then that is concatenated with A union epsilon. And that is going to get you all the way over to your final state. And that is your regular expression. You will observe that maybe this could be simplified. However, usually when we're doing these problems, we want to make sure that you understand the conversion properties, how to construct a GNFA, how to rip a state and repair it. We're not looking for regular expression simplification. So don't worry about having to simplify it as much as possible and prove that. As long as you've got a finished regular expression and it's correct, you should be good to go. Also make sure that you're obeying the state instructions that we provide. If we do not give you state instructions of the order of ripping, then do whatever makes the most sense to you.
Nice. Okay, so on to number 12. But before that, we wanted to take a detour and talk about the pumping lemma in general. So there's a little bit of confusion in general about what exactly you have control over and what do you need to prove for regular languages. So just to recall, we have the pumping lemma, which states that we have this pumping length P. And the idea is that for all words in a language L, where W is greater than or equal to P, we can break up the word into three components, namely, so W equals to X, Y, Z, these three words, where one, X, Y is within the first P characters, so it has to have length less than or equal to P. Y has to be non-empty. And for all I, X, Y to the I, Z is an L. Oh God. Sorry. Is an L. So the idea is that DFAs either have loops or don't have loops. So if you let P be the number of states in a DFA, and you have a word with more than P characters, it has to revisit a node twice. And that is a potential loop in a way. So we try to capture that loop with the idea of Y, like Y being the characters traversed in that loop. And the third part of the pumping lemma is essentially saying that no matter how many times you traverse the loop, that word must exist in the language. So you can traverse it 0 times, namely pumping down, and X, Y to 0, Z should be in the language. You can take it once, which is your original word W, or you can take it multiple times. And if the language is regular, then it is still, it should still be in the language. So then the question is, how exactly do we use the pumping lemma? So the first thing is that we use it to show a language is not regular. And in order to show it's not regular, we need to show that it is the pumping length itself doesn't exist. So we have to look back here and we have to show, so we show that it's for all W, and next we have to show that there exists X, Y, Z. And the reason why we say this is that in order to show that something is not regular, when we negate this expression, we do get to choose a W as a counter example. We recommend that you choose something that is variable in length of P, because in order to use property number 1, you're going to want to talk about the first P characters. So if your word isn't even a function of P, it's not going to be easy to talk about what the first P characters actually are. Then you need to show that for all Y, so for all splits of Y, that the pumping lemma is violated. And the reason you have to show that is because we bring in an existence of XYZ over here. So we need to show for all choices of Y that are valid, it is not possible to pump. And if you show that is true, namely the pumping length can't exist for any splits of a certain word W, then you've shown that the language is not regular. We recommend that you refer to the slides when trying to come up with a template, but we'll also go over it in number 12. Okay, so back to our scheduled content over here. Namely, we have number 12, which is to show that the language where W has more A's and B's is not regular. So for our proof, we're gonna assume that assume L is regular. Oh god. Sorry. Okay, so we're gonna have a pumping length P. And then we can select a word W. In my example, I'm going to select A to the P, B to the P minus 1. Now, why did I select A to the P, B to the P minus 1? Because the first P characters are all A's. So no matter what Y we choose, we know it has to consist of all A's because the first P characters are all A's. So now the question is how many A's we will manipulate, not what the actual string Y contains. So we say we can say that so by 2, namely y is not equal to epsilon, so y is equal to a to the k for some k greater than 0. So this means that there's a non-zero number of A's being taken. And since we're trying to show that we're trying to find a word where there's less A's than B's, because that's not in the that's not in the language, it seems reasonable to pump down, namely get rid of these KA's and see what that brings us. But x y to the 0 z is equal to a to the p minus k, b to the p minus 1. But p minus k is less than p minus 1, or is less than equal to p minus 1. So therefore, x y to the 0 z is not in the language L. And since we've pumped down this word and y was non-empty, any less A's in the word and it's not in the language altogether. So no matter what y we take, we can show that by pumping it down, it's not in the language, and therefore L is not regular. Yep, so that's 12.
Awesome. Okay, so for number 13, this one should be pretty free for everyone. But the basic strategy here is that you start with S, and now you basically want to make the substitution such that you can get the answer we're looking for, the string provided at the bottom of the problem. So immediately, we don't want to terminate. So I'm going to go with brackets L brackets. And then inside of L, you can choose S, L, and S can become semicolon, L can become S, and S can become S semicolon. There isn't really any complexity to these problems. You can just try it until it works, try and introduce the things you're looking for and that you need to construct your string. I like the way I structure my parse trees. I find them very easy to read and interpret sort of what's going on with the substitutions. You don't have to structure them exactly like this, but it should be obvious each substitution that's being made.
My bad, I was muted. Okay, so we're going to be looking at number 14. We want to define two CFGs that generate the language below. And we need to make sure to specify all the components, namely V, E, R, and S. Yeah. Okay. So the first language is going to be a to the m, b to the n, where such that m is equal to n, so identical. The strategy for looking at this word, we can write down an example word like AABB, is to observe that these letters are essentially in pairs if we build, oh, that's crooked. If we build inside out. So we can imagine that we have a variable and it kind of puts another layer of A's and B's on the sides. Otherwise, we can derive the empty string and then it'll terminate our process. So we can solve this using one variable. We're gonna have S and it's gonna become either ASB. So that places an A and B on both sides, or it can derive empty. And of course, V is just the start state. And these are our rules right here. S is our start state, and of course, sigma is going to be just AB. So that's the first one. It's fairly simple. Now, interestingly, we have also the second one. So this is like 14.2 over here. Where's this 14.1? Where we want to generate a to the m, b to the n with m not equal to n. Now, interestingly, there's such a small difference, but the actual solution is much longer. And the reason is because it's not as easy to maintain like a asymmetry than it is to maintain a symmetry within context-free grammars. So over here, we want to split up the word we want to split up the task into two parts. Namely, we want to look at a grammar that generates for values m less than n, and for a grammars that'll generate for values m greater than n. And then the idea is that we can take the union of these two context-free grammars, and we'll get a new one that generates both of these words. So the way you can do this is you start with S, and the start state will either choose case like, well, let's call this case L, and we'll call this like case R over here. So either you'll derive, oh, sorry, I flipped them. Okay, we'll call this case R and we'll call this case L. So either you can derive AL, you can derive RB, yeah, or AL or RB in general. Notice you can't derive epsilon because that would terminate with equal number of A's and B's. Now in the L case, we're trying to generate words that have more A's than they have B's. And we're already guaranteed to have one extra A because we added an A by default. So L can derive like ALB if we want. It can also derive AL, or it can derive epsilon. And notice that no matter what, either we'll always have less number of A's than B's, because whenever we generate a B, we generate an A, but we'd already generated an extra A to start out with. And when we're done, we can derive epsilon and it will terminate the process. Similarly, for R, we can also generate ARB, but this time we'll derive RB and epsilon, and we're always guaranteed to have more B's than we have A's in this case. Now, S is our union thing. So it starts from one star variable and it generates either case. And that brings the L language and the R language together for 14.2. So over here, just to kind of do the hands work, SLR is our variables. Sigma is still AB. Here's our rule set right here. And then S is going to be S. And that's 14.2. Okay. So let's take a look at 15, final one. Now we need to take our languages that we just looked at, namely like A to the M, B to the N for M equal to N and not equal to N. And we need to prove that they are both not regular. Some intuition for why they aren't regular is like, if you imagine you have a DFA and it has to read like this string, for example, the DFA needs to count how many A's it's seen, and then needs to count, or maybe uncount for that matter, how many B's it's seen in order to see if like indeed there are an equal number of B's as there are A's. But we don't really have infinite memory in a DFA. And we're not even capable of counting unless it's like a finite counting. So this won't work for all possible strings out there. Okay, but either way, let's use the pumping lemma and let's show that a to the m, b to the n for m equal to n is not regular. So start the proof over here. So we're going to assume regular for a second. And then we're going to say there is a pumping length p out there. So I'm going to select, in this case, just a to the p, b to the p. Keep it simple. Since we're talking about the first p characters, similar to number 12, we know it's going to be all A's. And so when we select it, so by 2, we know that y is not equal to empty. And by 1, x, y is less than p. So know that y has all A's in it. And then so this time we're going to pump up just because we pumped down last time. So x, y to the 2z is going to equal to, so x, y to the 2z is equal to a to the p plus k this time, b to the p. But notice that p plus k is not equal to p for k not equal to 0 as here. So therefore, the language L is not regular. So yep, I kind of skipped a few steps in terms of terminology here, but I covered it all in 12. Like I think this proof pretty much renders identical to the other one. So I'd recommend you look at that one if you're confused. But yes, L is not regular. Essentially, this time we pumped up and we're able to leverage, since we picked a to the p, our non-empty y has to consist of a non-zero amount of A's. We pumped that up, and since our language requires us to have an equal number of A's and B's, pumping up extra A's breaks that, and that word cannot be in the language. So L is not regular. Cool. So that's 15a, but we also have 15b, which is to show that the set a to the m, b to the n for m not equal to n is in fact not regular. So you can we can try to prove it using the pumping lemma. And what you'll kind of see is that it's just not easy to do, because no matter what you pump, unless you pump like a very I haven't personally seen a proof that works, but it's whenever you pump, usually it's still like in the language, and it's not easy to show. But what I recommend you do look at is within slide deck A, so 11A, slide 88. I recommend you look at this closure property proof that I'm about to show. And the idea is to use the closure properties and assume it's regular. And we can then relate the irregularity of a different language to show that this language is not regular. So recall in 15a that we just proved that a to the I, b to the I for all I is in fact not regular. So we look at the connection between these two languages, and we notice that one of them is talking about m not equal to n, and the other one is talking about m equal to n. So if we take the union of these two, they're kind of complements under like A star, B star. So if this is like A star, B star over here, namely all words that have A and then B, we can split it up into words that fall under our 15A language, namely M equal to N. So I'm talking things like AB, AABB. And then 15B has M not equal to N, well, which is like AAAB, AABBB, all that. So all like asymmetric pairs. So what you want to leverage here is the fact that under A star, B star, these two are equal. So if we take the complement of, so yeah, so let L be our language from 15A. So if I take L complement for a second, what is contained in it? So L complement has to contain stuff from 15B because it's literally not 15A, but it also contains other words. So it's going to contain 15B, and it's also going to contain, sorry, I'll put an example like this. It's also going to contain random words like BABA, it's going to contain AAABBB, AA, etc. So the words in 2 we don't want to include because these words they're not going to get us to 15B. But if we intersect it with A star, B star, that domain, then we're only going to get the words in 15B. So if we take L complement and intersect it with A star, B star, then the words that remain are words that are a string of A's followed by a string of B's, and they have to be asymmetric in nature, so they can't have M equal to N. Now the proof is pretty simple following it. So yeah, let L be like the lang from 15A. Assume L is regular. Then L complement is regular because of the closure properties. Oh my God. Okay, and then we know that A star, B star is regular, which is by definition. So then we know that the intersection of two languages must also be regular by closure properties. And we also know that it follows that the A to the M, B to the N for M not equal to N, oh my God, is regular. Because that is the language that we're talking above. These two are the same language. But the issue is that we just showed that 15A is not regular. Hence, there's no way that hence there's no way to actually prove it. There's no way there's no way that this language can also be regular. Did I do that right? Yes. Okay, cool. Yep. Yeah, that was the last problem. So Dan, you want to close this out?
Thank you everyone for following along. If you have any questions, a couple of us TAs are going to be hosting office hours tomorrow on Monday from 5 to 7. Otherwise, good luck on the exam.
All right, thanks.